In this video, I'd like to talk about defining the trigonometric functions using a more circular definition. And specifically, we will come to what's known as the unit circle and how the trig functions are defined on that. And we know from right triangle trigonometry that if we have a right triangle, we can define the trig functions on here, where let's say this is our angle theta, and we basically relate the side opposite the angle, as well as the adjacent and the hypotenuse of this triangle to the three trig functions. And we can remember those definitions with the saying so katoa, where, for instance, the sine function with this s is defined as the opposite divided by the hypotenuse of the triangle. So this angle theta, that is this angle right here, when we plug it into the sine function, this is equal to the ratio of the side across from the angle divided by the long side of the right triangle, which we call the hypotenuse. And similarly, we have the cosine of the angle, that's equal to the ratio of the adjacent divided by the hypotenuse, and the tangent of the angle is the ratio of the opposite divided by the adjacent. And these definitions are very useful, but they run into one main issue. What happens if theta is bigger than or equal to 90 degrees? What happens if theta is less than or equal to 0 degrees? And when we encounter these cases, let's say theta is 120 degrees, we would no longer have a right triangle, and these definitions wouldn't work. So we need to come up with a new way to define the trig functions so that we can extend this definition to basically any angle, positive or negative. And the way to do that is to use the coordinate plane. And we'll start by drawing a ray from the origin, and this ray, which terminates at the origin and goes on as long as we'd like, will have an angle measured relative to the positive x-axis. We can call this angle theta, and this ray will have some length, which we can call r. And let's say this ray terminates actually at the end of this arrow. We can turn this into a point. And the definition for our trig functions will be very similar to the right triangle definition, since we can actually form a triangle here, or we can just consider the x and y value of this point, and it's at a distance r from the origin. And let's say the sine function, we can define that as the y-coordinate of this point divided by r, its distance from the origin. Likewise, the cosine will be the x value divided by the distance from the origin. And the tangent function, tangent of theta, can be defined as the ratio of the y value compared to the x value. And we know that this definition makes sense because in the first quadrant, notice that we can create a right triangle here, and the definitions end up being the exact same definitions we had when dealing with right triangles. So for angles between 0 degrees and 90 degrees, we essentially reduce this new definition back to the old definition, where this is the opposite side and this is the adjacent side. But the advantage of this new definition is that we can now look at angles either less than 0 degrees or greater than 90 degrees. And let's say we look at the ray that is now in the second quadrant, and let's say it just goes to some point over here, where again these are the x and y values of the point, and it's at a distance r from the origin, and its angle now is this blue angle, and again we can call that theta, and this new angle is greater than 90 degrees. So we have effectively extended our definition of the trig functions to basically any angle we want. We can put this ray anywhere in the coordinate plane. In fact, if we draw a ray that's negative, so let's say something down here, and by negative, I do mean this angle. This angle theta is now less than 0 degrees if we count it going in the clockwise direction. However, we could also look at it if we go in the counterclockwise direction, and in that direction, it would be a positive angle. So the direction in which we measure this actually matters in this case. If we go counterclockwise, like I mentioned, we count that positively. And if we go clockwise, counting down from this positive x-axis, then we count that negatively. And one of the interesting ideas with angles is that we can represent them in infinitely different ways. Let's say this angle theta is 45 degrees. If we add 360 degrees to that, that will take us all the way back around to the exact same spot. So this angle here, where we added 360 to it, if we compute that, that would be 405 degrees. This is also equal to 45 degrees. In fact, we can add 360 as many times as we want. So this is also equal to 765 degrees, or we can even subtract 360. That will work as well. 45 minus 316 degrees would be minus 315 degrees. All of these angles are the exact same angle. There are infinitely many ways to represent the angle theta on this coordinate plane. So these definitions allow us to extend the trig functions to any possible real valued angle. And one way to simplify everything is to set this distance from the origin, r, equal to 1. And by doing so, we create what is called the unit circle. So let me make a little bit of room, and we can plot that as well. If we paste in a new coordinate plane, we can draw a picture of this unit circle. And we call it the unit circle since now our ray is fixed at a distance of 1. But if we were to essentially trace that out for all angles, I'm not doing it perfectly, but we would essentially create a circle centered at the origin where that circle has a radius of 1. And let me quickly draw that in. And again, the radius of the circle, its distance from the origin to the edge of the circle, this is distance 1. And notice with our definitions that for, let's say, the sine function, this reduces to y divided by 1, or just y. So the y-coordinate on the unit circle is the sine function, the sine of this angle here, theta. And for x, for the cosine function, this reduces to x over 1, or just x. And the x-coordinate on the unit circle is the cosine of the angle. And we can even simplify the tangent function, since notice that the tangent of the angle is the y value over the x value, but the y value is the sine of the angle, and the x value is the cosine of the angle. And this formula for tangent can be incredibly useful. And you might wonder why extending the definition of the trig functions is useful, beyond the fact that we can now plug in angles of any size, is that with this circular definition, we will see that when graphing the trig functions on the xy plane, what we get are these wave functions. And this is not drawn perfectly, but we will look at these in greater detail in later video. And you can imagine anywhere in nature or human engineering that we see waves, the trig functions are the best way to model those scenarios. And you see waves all over the place. So in later videos, we will get more practice actually using these definitions, but these new definitions allow us to define the trig functions on this unit circle.